So would you say there are specific chronic illnesses that are more susceptible to plasmalogen abnormalities, or do you see this across the board more or less? I know there's different profiles of plasmalogen deficiencies or abnormalities depending on the illness, but would you say this is something that is more or less equally distributed in terms of, like, if you look at it on most chronic diseases, you're going to find more or less a similar sort of scenario?
Well, there's two ways of looking at it. There's one is, which diseases does a plasmalogen deficiency contribute to, and which diseases are the disease actually depleting you of plasmalogens? Okay, so, and they overlap. Can you prevent disease? For example, for me, I take high-dose plasmalogens, and I think it's contributing to the fact that I rarely ever get sick. I can't think of myself getting sick. And many people, and it's like that one study I mentioned to you that they did with the alkylglycerols, that they took the plasmalogens as a preventative for getting the flu. And people who took the plasmalogens didn't get the flu. Those who did not got the flu. So it is definitely, you can shift the odds in your favor, right? Having extra reserve capacity can give you higher resilience. But there's like the CIRS and other kind of infectious type and autoimmune hyperactivity diseases. These are typically not caused by a plasmalogen deficiency. They actually they're the ones that are causing, they're depleting your plasmalogen levels. Okay, so those diseases are they're just sucking your plasmalogens down. Now, diseases where as you get older, your ability to make enough plasmalogens, like your peroxisomal function, can decline. So Parkinson's, Alzheimer's disease, some cardiovascular diseases, these are going to be caused, they're the low, if your body stops making enough or you start becoming deficient in them, then the plasmalogen deficiency directly contributes to those diseases. And Alzheimer's is kind of like the canary in the coal mine. The cholinergic system, and frailty, of course, as well, the cholinergic system appears to be exquisitely sensitive to low plasmalogen levels. And the cholinergic system is what drives our executive function. And so that's why, of the age-related diseases, the highest association of a future disease caused by or contributed to by low plasmalogens would be dementia, followed by things like Parkinson's, and that have, and then multiple sclerosis is more of a mitochondria-related issue, where the high plasmalogens can restore that white matter and prevent future white matter deficits. But it's a disease like multiple sclerosis or autism, where you have fundamentally a mitochondrial insufficiency that then leads to a pro or a chronic inflammatory event, like an autoimmune inflammatory event. And then that eventually overwhelms their endogenous capacity to make the plasmalogens. So it's kind of, it can come from different directions depending upon your personal circumstances.
Yeah.
In the end, though, basically the mortality, the longevity, having low plasmalogens is basically just not worth the risk, right? So you kind of want to have, you want to keep your plasmalogen tanks full. That's one of those molecules or one of those nutrients that you just don't want to be deficient in.
Yeah. So it sounds, based on what you said, that there's sort of two pathways depending on the illnesses, where you either have some sort of a more quantitative element where it's like either a deficiency and that's causing disease, or something more functional where it's like you mentioned the mitochondrial dysfunction. I would say CIRS is probably in the category of mitochondrial dysfunction, and there's now a lot of there's a test that we use. It's it's not clinically diagnostic, but practitioners are using. It's called the Gini test, and it looks at transcriptomics and different biomarkers that become either upregulated or downregulated very consistently in CIRS patients. And one of the things that we see is metabolic abnormalities. So we see a lot of markers that are sort of indicative of aerobic glycolysis and metabolic acidosis and suppression of mitoribosomes, where sort of ATP production is impaired, and so that goes hand in hand with metabolic acidosis. And we've been able to identify specific triggers in the environment, or specific bacteria in this case, that seem to be inducing that shift in cells. And but that's one. So that, when you see that in CIRS, well, that's very much like a functional problem. And so what you're saying is that something like that, essentially what it can do is deplete your plasmalogens.
Correct.
Over time. Right. And in that context, would you say plasmalogens are sort of, they're sort of, could be considered as almost first line defense in terms of the cell membrane and protecting it? And is that why when you have a deficiency, you may end up having something like CIRS, which is an immune reactivity? It's specifically from the innate immune system, where you're seeing that immune reactivity, at least initially. Eventually can spill over into autoimmune disease. There's a lot of CIRS patients who can end up with multiple sclerosis. It's more of like a downstream problem, but it all starts with the innate immune system. Yeah.
Well, let's dig into that a little bit more, because mitochondrial function is core. Like, so all the oxygen in your body, which, if you say oxidative stress, it's oxygen, right? It's oxygen being converted into inflammatory molecules. The biggest one is hydrogen peroxide, and then peroxidated membranes. And so anytime that you have any kind of oxidative stress, and you talk about the anaerobic lactic acidosis type situation, right? So all of that all comes down to an insufficient mitochondrial capacity. Okay, so any time that you have elevated, say, malondialdehyde levels, elevated oxidative lipids, any of those things, it all comes back to an impaired mitochondrial capacity, right? And this is where, as we get older, maintaining skeletal muscle mass, maintaining, mitochondrial things that stimulate mitochondrial capacity are critical to maintain as we get older. And so when you start digging into that stuff, so what happens? So all of these inflammatory diseases end up becoming from the mitochondria. So regardless of where it starts. So here's what happens. So say you have an infection, whatever it is, right? That infection creates a stress on the body. Typically what will happen is your cells, your microglia, your macrophages, they're designed to go seek out damaged cells. And how the immune system recognizes that a cell is damaged is one of two things. Either it has a protein tag, like it's like a virus-infected cell or a bacterial-infected cell that is identified by one of your immune cells, or you have a more of a generalized oxidized membrane. Okay, and that is what stimulates the immune system, especially in the brain. The microglial inflammatory cascade in the brain is almost entirely, like, the brain is pretty immune to actual virus and bacterial particles. Like, there are certain circumstances where that happens, but not a lot, right? So the inflammatory nature of the brain is all oxidative stress related. So what happens is the mitochondria get overwhelmed, and then the oxygen that's going into that mitochondria is not being converted into water. So when we breathe, our body, we're bioreactors. So we take in oxygen from the air, we take in carbon supply, carbon backbones from the food supply. We burn that into carbon dioxide and water. So the oxygen that we breathe gets burnt, just like octane in your car engine does, and the carbon dioxide is supposed to convert into carbon dioxide and water. When oxygen doesn't get converted to water, it gets converted into other side products, like peroxide membranes. So what plasmalogens do, one of the biggest things plasmalogens do is they neutralize the peroxide so hydrogen peroxide in the peroxidate membranes. So the benefit that you're seeing from the glia, okay, a lot of it is just sucking up all these peroxidate membranes and neutralizing them. And that lowers the immune stimulation response. You're taking away the stimulus of the immune system. Okay, so you're removing that stimulus that the immune system is reacting to. And you're simultaneously refilling up the membrane structure itself. So the first phase of immune or a chronic inflammatory syndrome is to clean up the peroxidated membranes, which is actually relatively easy to do. And that's one of the systems that you're seeing when you take the plasmalogen precursors like prodrome glia. The other thing that people might notice, like when you're in these really hypersensitized states, I always tell people to be careful. You can go slow. Sometimes you need very little amount at first, right? Other people can take large amounts of plasmalogen precursors, but they're also going to make your dormant cells active again sometimes, right? Because when people talk about senescent cells, cells that basically turn off, they're still there, they're physically contained, but when the membranes get oxidized, the phospholipids in the membrane get all chewed up, and the cells become stiff and shrunken, if you will. This is what people call like senescent cells. Like they're hanging around. They're not dead, but they're not alive. They're kind of zombie cells, right? But when you can actually start reactivating them, when you start fixing the membranes of zombie cells, they no longer become zombie cells. So they can actually activate a little bit. So sometimes people need to go in a wave formation where they take some on, off, and it kind of gradually cleans your system of it. So don't be afraid if you've taken a plasmalogen precursor and you feel like you've had a rebound effect. You just kind of go slow and take it. Then stop taking them for a little bit and then go back again. Because sometimes if you're flushing these cells out of your body, one size doesn't fit all for everybody. And the cool thing about these kind of molecules is that you're in control, right? Like if you stop taking them, it goes away, and then you put them back in again. And so don't listen to your body, okay? Don't override intellectually what you're actually feeling inside, because it should gradually work its way through. We see that sometimes with especially when because your body adapts. Okay, when you're in a hyper-inflamed state, your body will shut down from that inflamed state, and it adapts to it. And then when you reactivate it, all parts of your system don't catch up at the same rate. And so you kind of got to give parts of your body time to catch up to the reactivation.
Right. Yes, that makes sense.